Good evening, Year 11, and welcome to your night before your physics exam video. And for many of you, this will be your last exam, so good luck. So, paper 2 covers the following topics: waves, forces, and electromagnetism. Additionally, if you've done triple science, it will also cover the space physics topic, although I'm not mentioning that on this video. So, our first visit will be to the waves topics. And what do waves actually do? Light is a wave, sound is a wave. They are both methods of transferring energy from one place to another. And that is all waves are. They are just a means for energy transfer. And as they travel through a material, they cause that material to vibrate or to oscillate. Once the wave has travelled through that material, those vibrations cease. So the material is only vibrating whilst the wave is travelling through it. But these two types of wave are slightly different in the way that they operate. Sound, for example, is an example of a longitudinal wave. And that is where the direction of the vibration of the material is parallel to the direction of the energy transfer by the wave. So in this case, with the slinky, you can see here, the coils on the slinky will move to the left and right, and the energy is being transferred in exactly the same direction. Light, on the other hand, is an example of a transverse wave. And that is where the direction of the vibration is perpendicular to the direction of the energy transfer. So the wave moves in the up and down direction, but the energy is still being transferred from left to right. Once the wave has gone through the slinky, it returns back to its original position. So those two types of wave are our two main types. Sound, as I mentioned, is a longitudinal wave. The other type of longitudinal wave that you may come across is a P-type seismic or earthquake wave. They are the initial shock waves that happen after an earthquake, and they cause the sort of jolting motion that you feel through the ground. Transverse waves, though, are a more extended bunch. So all of the electromagnetic waves, all of the different types, are all transverse. Water waves are transverse, and the S-type seismic waves are also transverse. These are the ones that make the ground move up and down and make buildings sway from side to side. The electromagnetic waves, though, are a special type. They are the only ones that are able to travel through a vacuum. Every other type of wave needs a material to travel through, but electromagnetic waves can travel through empty space. And we'll be looking at those in a little bit more detail now. So this diagram here shows the complete electromagnetic spectrum. There are 7 different types of electromagnetic radiation, and they correspond to particular wavelengths and particular frequencies. All of the 7 different types travel at the same speed, the speed of light, which is 300 million meters per second in a vacuum, or 3 times 10 to the power 8 meters per second if you're using standard form. Radio waves on the left are the ones with the largest wavelengths and the smallest frequencies. Gamma radiation on the right is the one with the shortest wavelength and the largest frequency. And as you move through the spectrum from radio to gamma, the wavelength is constantly decreasing, the frequency is constantly increasing. The visible part of the spectrum is a very small section in the middle there, which I've expanded out at the bottom, and you can see the different colours of the visible spectrum. So red light has the largest wavelength and the lowest frequency. Violet light has the smallest wavelength and the highest frequency of the visible part of the spectrum. You are expected to know the order of the electromagnetic spectrum. You can get questions on the exam where they give you part of it and ask you to fill in the missing ones. For those of you doing higher tier, you may be also expected to know of some uses for the different parts of the electromagnetic spectrum. So radio waves are obviously used for communications, both radio and television. Microwaves are used for mobile phone communications and also for heating up food in a microwave oven. There are a few very specific frequencies for that. Infrared radiation is the type that we feel as heat. So we use infrared radiation, for example, in heaters and in toasters to cook food, and also in thermal imaging cameras to detect infrared radiation being given off. Visible light is the type that we can see, so our main use for that, other than obviously being able to see things, is in television screens and in fibre optics. Ultraviolet light is used for security marking, for tanning purposes, well, suntan beds for those of you that have ever tried them. X-rays are used in hospital environments for taking pictures of the inside of your body. And gamma radiation is used in the treatment of cancer. Gamma radiation can be very dangerous and it can kill cells, but in a targeted way, we can use it to our advantage. As you move through that spectrum from radio to gamma radiation, going up in frequency and down in wavelength, the energy associated with those waves also increases. Radio waves have the least amount of energy, gamma radiation has the most. These three radiations at the top end of the spectrum, ultraviolet, X-ray and gamma radiation, are also referred to as ionizing radiation. That means that when your cells are exposed to them, they can be damaged because they can ionize some of the atoms that make up you. Ultraviolet radiation is the least dangerous, it's the least penetrating. So a high dose of ultraviolet radiation in the first instance can cause things like sunburn, it can cause premature aging of the skin, it can cause irritation to the eyes. In a more extreme dose or over a longer period of time, it can be responsible for skin cancer, but not any other type of cancer, as it is not penetrating enough, so it can only penetrate the skin. Large doses of X-rays and gamma rays can obviously damage the DNA and can lead to mutations which can cause cancerous tumours to grow. Gamma radiation obviously being more dangerous than X-rays. Equally though, they do have some uses, as we talked about. X-rays can be used to observe the bones inside your body. So very low doses of X-rays can be used to look inside of you without having to cut you open. Gamma radiation can also be used to sterilize food and to sterilize medical equipment because the gamma radiation will kill off any microorganisms that are present without actually damaging the food or the medical equipment. And as I said earlier, it can also be used to treat cancer. Okay, moving on to forces. Forces, you should remember, are shown by arrows on diagrams. They show the magnitude of the force, how big it is, and they show the direction the force is acting. So a large arrow would represent a much larger force than a smaller arrow. When you're showing forces acting on objects, we generally have them acting from a point we call the center of mass. Imagine an object has been crunched down into a small point mass, and wherever that is located within the object, that would be its center of mass. If you're asked to draw force diagrams, it's very important that you label them with the name of the force. A couple of key points to remember: weight always acts downwards towards the center of the planet or the Earth if you're on the Earth. The normal reaction force, as you can see here, always acts perpendicularly upwards from the surface. Other forces can act to the left and to the right, but it's important that you put the names on them to show which force they are. Force diagrams are also meant to be scale diagrams. So if you're asked to draw forces of a particular size using a particular scale, then make sure you read that information to know exactly how big you need to draw your lines. Okay. Moving on. The resultant force is the sum of all the forces acting on an object. So if we take a look at this example here, we can see there's a person at the front pulling the trolley and there's a person at the back pushing the trolley. They are both applying a force of 10 newtons each, but they are going in the same direction. So when forces act in the same direction, you just add them together, and so the resultant force acting on this trolley now is 20 newtons. However, in this example, the forces are acting in opposite directions. The little stick man there is pushing the box to the right, but there is friction acting to the left. When you have forces acting in opposite directions, the resultant force is the difference between the two forces. So it's the big force, take away the smaller force. The direction of the resultant force would then be in the direction of the larger of the two forces. So as we can see here, we had a 20 newton force going to the right and a 15 newton force going to the left. So the resultant force of 5 newtons is going to the right. Now, the resultant force is important when it comes to the motion of the object. If we take a look at the car here, it's got two forces acting on it that are equal, and so the resultant force acting is 0. And when the resultant force is 0, it means the motion of the object will not change. So if this car was stationary, it would stay stationary. If it was moving, it will keep moving with a constant velocity. That means at the same speed and in a straight line. It's important that you use the words constant velocity to describe this arrangement, as it is much quicker and easier to write than constant speed in a straight line. If the resultant force acting on an object is not 0, then an object will accelerate, and it will accelerate in the direction of the resultant force. So if we take a look at the two forces here, we've got 500 newtons going to the left, 700 newtons going to the right. That means our resultant force will be 200 newtons. Therefore, that car will be accelerating to the right, or in this case, forwards. Another application of forces that you need to be aware of is terminal velocity. Terminal velocity is the maximum speed that something will reach. So if we take a look at an example of a car moving here, the engine is providing a thrust force going in the forward direction of 8,000 newtons. Air resistance and friction are providing a drag force of 1,000 newtons. So there is a resultant force acting to the right, and that will cause the car to accelerate. However, as the car accelerates and its speed increases, the air resistance also increases, and that now increases to a much bigger value. There is still a resultant force acting to the right, but it is now smaller. Therefore, the car will accelerate at a slightly slower rate. But it's still accelerating, it's still getting faster, but just not as quickly as it was before. However, eventually, as the car speeds up, the resultant force acting on the car will drop to 0. The friction and the air resistance will balance the thrust from the engine, and so the resultant force acting on the car is now 0. So it will now move at a constant velocity. It has reached a maximum speed, and we call that speed the terminal velocity. Now, Different objects will have different terminal velocities based on things like the thrust from their engines or their shape. Air resistance has a different effect on different shapes. So if we imagine the same size engine now being in a truck, so there you can see still an 8,000 Newton force, the truck has a much larger surface area, and so the effect of air resistance on it is much bigger. So the lorry, although it has the same engine as the car, because it has more air resistance, its air resistance value there you can see is much bigger. The resultant force acting on the lorry will be smaller. It will continue to it will accelerate to the right, but it will accelerate at a slower rate than the car. And as it speeds up, that air resistance force increases much more rapidly. And so it will reach the situation where the forces are balanced at a much lower velocity than the car did. So even if they have exactly the same engine powering them, the car will be able to achieve a higher top speed because it will be able to accelerate to a higher velocity before the two forces are balanced, whereas the lorry will not be able to reach such a high speed. Similar situations happen with parachutists. The weight coming down is balanced by the air resistance going up, and then when you open your parachute, the air resistance increases, which slows you down, and so that you don't hit the ground at such a fast speed. So car engines and parachutes are the two main examples where terminal velocity appears in exam questions. Moving on to the magnetism topic, and you should be aware of the shape of a magnetic field produced by a bar magnet. The magnetic field is always in this arrangement as shown in the diagram. So there are field lines that come out from the North Pole, loop around and go back into the South Pole. You should show arrows on some of your field lines to show the direction of this magnetic field, and it always runs from north to south. The magnetic field lines are closer together where the magnet is the strongest, so in this case at the poles. If you're asked to show magnets with different field strengths, then you would need to draw a different number of field lines on each diagram. When magnets interact, their magnetic fields interact. So when you have two magnets that are attracting each other, so opposite poles of the magnet, then the field lines join together. So the magnetic field lines coming out of the north pole of one will join directly on to the south pole of the other, which means in between the two magnets you get an area of a very strong magnetic field. However, if you have two magnetic poles the same facing each other, their magnetic field lines will repel each other. They do not cross. And in between them, at the point labelled P, you can see on the diagram there, you will get a region where there is no magnetic field because the magnetic field lines aren't going through it. So we have these two types of special cases where magnetic fields interact. We also have magnetic fields for other situations, which we're going to look at next. Okay, there are two more situations where you need to be aware of the magnetic fields. The first is the magnetic field of a straight piece of wire that is carrying an electric current. That produces a circular magnetic field with the magnetic field lines being shown as concentric circles. They are closer together near the wire and get gradually further apart as you move away from the wire. That is because the magnetic field is stronger when you're close to the wire. The direction of the current when we're looking at magnetic fields is the conventional current. So it's the current that runs from the positive to the negative. All of the laws of electromagnetism were written when we thought the electric current ran from the positive to the negative. So to work out the direction of the magnetic field, if you use your right hand and stick your thumb out, as you can see in the diagram here, Your thumb points in the direction of the electric current from positive to negative, and the direction your fingers are curling is the direction of the magnetic field. So that is the magnetic field of a straight piece of wire. If we take that straight piece of wire and coil it up, then we create a device called a solenoid. A solenoid has a magnetic field that is very, very similar to that of a bar magnet. It has a pole at either end. The magnetic field lines come out of one end, loop around, and come back in at the other end. Inside the coil, the magnetic field is described as strong and uniform. You can see that the field lines are all very, very close together and they're all equally spaced. Now, for a solenoid, you can make that magnetic field stronger by increasing the current in the wire or increasing the number of coils in your solenoid. One more addition we can make to this one is if we place a metal rod made of iron or steel inside that coil of wire. That metal rod is known as a core. It does need to be iron or steel. It won't work with other metals unless they are magnetic. In this arrangement, we have produced something called an electromagnet. And like the solenoid, the magnetic field of the electromagnet can be increased by either increasing the current or increasing the number of coils. But this arrangement has a much stronger magnetic field than the solenoid coil by itself. Electromagnets, though, have got some advantages over ordinary permanent magnets, and that makes them very, very useful. So those advantages include the fact that you can switch them on and off. So by switching the electricity off, it stops being a magnet. Very useful if you want to pick things up and then be able to drop them. With a permanent magnet, they're always stuck to it. With an electromagnet, you can switch them off and you can drop them. Think scrap yards where they pick up cars, and some of those arcade machines with similar to a sort of grabby claw mechanism where you use magnets to pick them up. The other advantage is that you can vary the strength of the magnetic field. By increasing or decreasing the current through the coil, you can make the magnetic field as strong or as weak as you need it to be, whereas with a permanent magnet, it always has one fixed strength. The other thing that you can do with an electromagnet is that you can change the direction of the magnetic field by changing the direction that the current is flowing through. And making electromagnets is a relatively cheap and easy process in comparison to a permanent magnet. So you can use wire and a power supply and any piece of iron or steel to make an electromagnet. So some of the basic advantages. So continuing on with the electromagnetism topic, and this is for higher tier students only, is the motor effect. And this is something that happens when you have a current carrying wire being placed into a magnetic field. So the piece of wire has a magnetic field around it as a result of it carrying a current, and that interacts with the magnetic field of the magnets around it. And as a result of that, the wire experiences a force which makes it move. This is our motor effect. So the current in the wire interacts with the magnetic field and that produces movement. Now, in order to determine which way something is going to move, we use Fleming's left-hand rule. So if you hold out your hand and position your fingers in the directions as shown here, so that they are all perpendicular to each other, your index finger is pointing in the direction of the magnetic field from north to south. Your middle finger is pointing in the direction of the conventional current, so from positive to negative. And in any exam questions that want you to use this, they will show you a power supply or a battery, which will have the positive and negative sides labelled so that you can see which direction the current is going. or there'll be an arrow to indicate which way the current is going. And then your thumb will be pointing in the direction that the force is being experienced. So if a question about this comes up in the exam, don't be surprised if you see people sitting there with their hand in this position trying to work out the other one. Okay, and moving on to momentum. So coming back to forces, momentum is again something that is for higher tier pupils only. And it is a property of moving objects, and it is affected by the mass and the velocity. So as you increase either of those things, the momentum increases. If an object is not moving, it has zero momentum. Also to consider is the fact that momentum is a vector quantity, like forces. It has a magnitude and a direction, so we quite often represent it by arrows. It is conventional to go upwards and to the right in the positive direction and going to the left or going downwards as the negative direction. It doesn't matter as long as you're consistent. Okay. The other thing to consider is that momentum is a conserved quantity. That means the total momentum before and after any interaction or collision between objects has to be the same. However, there is one small caveat to go with that, and that caveat is that this only applies to a closed system. What we mean by a closed system is that there is no energy entering the system from outside, there is no energy leaving the system, and there are no additional external forces acting other than those forces between the objects involved. So when dealing with momentum, there are some particular types of situation that frequently get looked at. So the first type of situation is where you have a initially stationary object which moves apart. So a gun being fired, so the bullet comes out of the gun and the gun recoils, or in the case we've got on the screen here at the moment, we have two people standing still on the ice on ice skates. So at the moment they have zero momentum because they're not moving. However, if they push away from each other, they will then have momentum going in the opposite directions. Now, I've assumed for the purposes of this example that they have exactly the same mass. So the person on the right will move to the right with positive velocity. The person on the left will move to the left, therefore they will have negative velocity. And so the momentum, mv, is exactly balanced by the momentum of the second person minus mv. So when you add their two momentums together, the total momentum is still zero as it was before. Momentum has been conserved. The other situations that can come up involve collisions, and those collisions can be between vehicles, they can be between people. Ice skaters have come up previously, colliding into each other, cars colliding into each other when either one was stationary or when both were moving, sometimes going in the same direction, sometimes going in opposite directions. So if we take a look at the example here, before the collision, the total momentum of the system is just the momentum of the lorry, its mass multiplied by its velocity. The car has no momentum because it's stationary. So when the lorry collides with the car, and the two things stick together, the total mass of the system has now increased slightly because we've got the mass of the lorry plus the mass of the car, but the total momentum is initially conserved. And as a result of that, the velocity at which the two objects will move away to the right will now be smaller. So the mass has increased, the velocity has gone down, but the total momentum is still exactly the same. The other situation is where you have two objects that are moving towards each other. So in this case, we've got a big lorry moving at a slower speed to the right and a smaller car moving at a larger speed to the left. So if you work out the momentums of the two objects and then add them together, remembering that one of them is going to be negative, it's entirely up to you which direction you pick as being the negative direction. I would always go to the left. So the total momentum is then going to be the sum of the two initial momentums. If the two objects stick together, as shown in the second picture here, then the total momentum of those two objects will equal the momentum before. Now, depending on those momentums will determine whether or not the object actually moves. If the lorry and the car had exactly equal but opposite momentums, when they crash into each other, they will both stick together and become stationary. If one of the momentums was larger than the other, then when they collide and stick together, they will move off in the direction of the larger momentum. So that is always the case with momentum. When two objects are colliding, if they were going in opposite directions, the momentum afterwards is in the direction of whichever one had the largest momentum. If they had exactly equal but opposite momentums, then that means the total momentum before was 0. So the total momentum after has to be 0, and therefore the object would not be moving, or the combination of objects in this case. Okay, and that is it for tonight. So good luck with the rest of your revision and good luck with your exam tomorrow.